Sometimes we just need a little bit of lightheartedness to start off. After that, what we get is chapter 8 and chapter 9. This is looking at the mole concept and reactions and how all of those things come together. So when we talked about how dimensional analysis and following a process, like our textbook outlines, is important, this is where it becomes important. If you've been breaking things down into individual steps to do solves, you're going to have a really bad time in this section. The whole point of that last section was to trust that this method works. Okay. That said, let's go ahead and start into it. So let's get used to our brains working and functioning with this metric unit conversion. So step 1, what are we solving for? We're solving for micrograms. Step 2, what are we given to start with? And a slight modification of that start, we're going to work our way right to left as opposed to left to right. We're starting with 325 milligrams of aspirin. This is one given piece of information. So we're going to put it here as one piece. Okay. Why am I placing that 325 milligrams in the numerator? Well, milligrams is a measure of mass, micrograms is a measure of mass. The mass unit is in the numerator in my answer, which means the mass unit needs to be in my numerator in my work. Milligrams is not the same as micrograms, so since I know milligrams needs to be canceled, I'll place it in the numerator, and then ideally I would have micrograms appear in the numerator. So we might go, okay, well, let's just find that conversion. And what we will likely find is that micro means 10 to the negative sixth. Okay, if we look at the cover page of most of my exams, we've got micro unit equals 10 to the negative sixth unit. What does this mean? In this case, it would be micrograms equals 10 to the negative sixth grams. So 1 microgram is 10 to the negative 6 grams, not milligrams, which means that conversion factor, as we've written it in our orange, does not exist, so we have to come up with a new one. Okay, so what could I convert milligrams to? The easiest thing to convert to would be grams, and if I did that, I could then see that I have the potential to do a gram to microgram conversion. So what did we say is that one piece conversion? That's one you're required to know. Milli means 10 to the negative 3. Power of 10 always goes with the core unit. 10 to the negative 3. And we could now look at to see that our units, or what's happening with our units, our milligrams cancel. We're not at micrograms yet. So I can go ahead and move to another conversion. In that other conversion, I want grams in the denominator so that my grams can cancel. And ideally, I would get micrograms. Do I have that conversion? Yep, I do. 1 microgram is 10 to the negative 6th grams. Notice again the power of 10 going with the core unit. Okay, I don't have to know relationships between those sizes. Now that I've got all the math set up, the only unit left in my calculation would be micrograms, which means I could now run through and do the calculation. I have 1 times 10 to the minus 3 times 325 all over 10 to the minus 6th. I can go through and enter it into my calculator, and what I should get would be 325,000 micrograms. So a really, really, really large number. Okay? And there we have it. We've got our conversion. So that's our basic process behind how we move it. The thing that's going to become more challenging in this next system is that you're responsible for finding those conversions. Okay? So next thing I want to throw at you, just so that you're aware of it, is that we could go through and really push these conversions. For instance, if I asked you to convert, 2,437,000 inches into miles, but you can only use alphabetic symbols, the process of doing so is what you should be getting used to. Okay? If we did that, there you go. Notice that there's only alphabetic symbols, no numbers actually written down. And what this goes through and shows is the solving process. That's what you should be getting used to. Not the steps, the calculations that you're doing, but why you're placing numbers where you want to place them. Okay? So if you want to read that, you can pause the video and feel free to go through and read that. It's at least half decent. Okay? But more important, what we're going to do is move into looking at our formulas a little bit closer before we push even further on. So, if I wanted to build a wheel, I need spokes and a rim. Okay, and officially, a tire on it. So we've got this tire out here. We've got a rim in here. And then we've got all of the spokes on the inside. Okay, so those spokes, depending on the tire, we're probably looking at 32. Let's just say 32 just for the heck of it. So I could go through and explain how to build out a wheel. And we could go through and just say, well, this now equals a wheel. So we could say 1 tire plus 1 rim plus 32 spokes becomes 1 wheel. Well, chemists recognized that we could do this, and it theoretically works, but there's a scalability issue here. When we build things out this way, we have to create a new name for each of those pieces, and each of those pieces then needs names when they build out to larger and larger things. And as long as we look at relatively simple few things, this naming system works. But in chemistry, we're literally describing the pieces that make up everything known in existence and everything that we haven't yet discovered. So the sheer numbers of things means we would have to have an infinite different number of, or infinite different names for each of those pieces, and we would then have to memorize all of those pieces. So what we shifted to was coming up with a different system where we simplified and say, instead of writing out the whole name, we could just write a symbol for it. Okay? Just a one-letter symbol for it. And this simplifies things a little bit for us. Okay? And then it becomes, and we could then go through and say again 1 wheel, but that still doesn't fix that system. So what we went through and did instead was we recognized that new thing was a combination of the previous, and we get 1 TR spoke 32. Okay? And we now have a way to represent wheel referencing the constituent pieces. Okay? Where this becomes useful is we now have a way to numerically show the relationship between these. So that if I wanted to build 1 wheel, okay, or in this case 1 TRS32, what would I need? Well, to make 1 TRS32, I need 32 spokes. Okay? And for those of you being like, well, but you also need those other pieces, that's true, but in this case, all I'm asking about, or all I care about, is the spokes. Why? Because that's what the question asked for. It allows me to simplify. So this is relatively simple, and you could probably come up with it easy. If we followed the methodology that we went through and talked about, we're saying I want 1 spoke from 1, or how many spokes do I need from 1 TRS32? Well, what is the relationship between TRS32 and spokes? Well, that conversion, that relationship there, comes from the chemical equation. So 32 spokes, 1, I multiply it out and I get 32. So at this simple level, you're like, why do I need that process? Why do I need dimensional analysis? Okay. The issue that you're encountering there is that you're assuming that this scale works in all cases, and it becomes trivial to deal with. What happens if instead of working with just 1 tire, I want 32,000 tires? Okay, so if we don't use the simplified equation to generate this conversion factor, we now have to scale this equation up to each of these larger and larger systems. Okay, and even 32,000 really isn't a big deal. Okay, in the grand scheme of things, that's tiny in comparison to the amount of atoms and molecules that are generated through chemistry. So what we're trying to do is create a system that allows us to manipulate and understand those relationships and ultimately come up with conversion factors that we can use when the numbers at we're either solving for or that we're given become absurdly weird numbers that our human brain can't deal with. Okay? So if we go back again to our formula, the whole point of that formula allows us to generate conversion factors. I can see that to make 1 TRS, I need 32 S's. To make 1 TRS, I need 1 tire or 1 T. Okay? So recognizing the information embedded in that formula will help us to create conversion factors that we can use to relate different substances with each other. Okay? Which then kind of pushes to the same kind of thing if we scaled this out to chemistry. Sodium carbonate. If I want to make 1 sodium carbonate, I need 2 sodiums. That's what the formula means. It gives us that numerical relationship. And what we've identified in each of those cases is a numerical value, a number, and a substance. The thing that's kind of missing is what is the measurement in this case? Well, in the case of sodium, it would be an atom. 2 atoms of sodium are needed to make 1, well, it's not atoms anymore because those are complex, molecule of sodium carbonate. So we kind of imply some of that naming or that labeling aspect behind those pieces, but that's embedded behind this. Okay, so if we scaffold this out a little bit, let's look at some potential models. Okay, how many atoms of sodium are needed to make 1 molecule of sodium carbonate? So 1 molecule, you'll notice I'll write MLC because I don't want to write out all of the molecule of sodium carbonate. How many atoms? Whoops. Helps if we flip this around. What are we being asked to solve for? We want to know the atoms of sodium. And what were we given to start with? We were given 1 molecule of sodium carbonate. Well, what's the relationship between the molecules of sodium carbonate and the atoms of sodium? Well, that information comes from the chemical formula. So our chemical formula gives us that information, and it tells us that there are 2 atoms of sodium in 1 molecule of sodium carbonate. So now when we run through the conversion, we get 2 atoms of sodium. Cool. That's the whole point of it. It allows us to do that conversion. And for those of you being like, well, I didn't need all the work to do that. That's true, you don't. What you do need is the process so that when we scale this out to absurd systems, you now have a process that allows you to manipulate this more easily. Okay? So let's try it again. What is the mass in grams of sodium needed to make 1 molecule of sodium carbonate? So we can again set up our system and say, well, I want I want grams of sodium, and I am starting with now 1 molecule of sodium carbonate. And we set up the conversion just like we did before, sodium carbonate and sodium, and we might go through and say, well, this is just 2 to 1, like we've been following these patterns. But again, this is why it's important to include the substance in this. How, 2 what of sodium? 2 atoms of sodium make 1 molecule of sodium. Okay, and why is that an important thing to address? Well, if we go through and look at this, molecules of sodium cancel. What unit will we have? We'd have atoms of sodium. What did I want? Grams of sodium. Those are 2 different things. Okay? And to give you an idea on why those are 2 different things or how they are 2 different things, think about it back to, bread. If I give you 2 slices of bread, does that mean you have 2 grams of bread? Does that mean you have 2 pounds of bread? 2 kilograms of bread? Okay? Mass and number are entirely separate systems. Okay? A chemical equation gives us the number of things. It allows us to build on it quicker and easier. Okay? But mass is what we really need to weigh out because we can't count easily. Okay? So we have to be aware that there's a disconnect. The conversion factor found in a chemical equation is not mass. It is a counting. It is a number of those particles. Okay? So if we're now going to try and solve this out, we would need the relationship between an atom of sodium and grams of sodium. Okay? So we would need that extra conversion factor. Now we have a potential issue. Okay? That potential issue is that atoms are really, really, really tiny. Okay? And that if I look at a single atom of sodium, the gram value is so astronomically tiny that I can't measure it. So that conversion, while possibly existing, I can't deal with it at that scale. Okay, which means when we go all the way back to the initial question, molecules of sodium, a single molecule of sodium isn't something I can get a hold of, or even a molecule of sodium carbonate. So how do we deal with this issue of scale? Because my chemical reaction gives me the number of pieces that go in. Mass is how I weigh things. But when I look at a chemical reaction, the numbers I'm seeing are really, really, really small or easy to work with, 1 through 10. But the grams that would come out would be powers of 10 negative. Okay, so just astronomically tiny. How do I reconcile those systems? That reconciliation comes in with what is known as Avogadro's number. Okay, and we're going to make some adjustments to this, which really I should have made before recording the video, but we're beyond that point now. So what this adjustment is that 1 mole of things, okay, and we'll address things in a second, is equal to 6.022 times 10 to the 23rd of those things. Okay? And as you may have heard, moles is something that chemists tend to freak out about and be like, oh, it's the greatest thing ever. Okay? So that must mean that I'm a horrible chemist because I don't think it's something worth freaking out about and pushing. The beauty of this conversion factor is that we don't use it. Okay, left a little dramatic pause, let that sink in. This conversion factor is literally designed so that I don't ever have to use it. That's the point. Okay? What are things? Okay? Things are an object. Okay? So molecules are things. Okay? Eggs are things. Atoms are things. There's tons of objects that we could be referencing as a mole of things. Okay? What might be more important is to note what is not a thing. Measurements. Measurements are not things. They are a measurement of a thing. They are a descriptor of a thing. Okay? If we consider measurements, they're almost like adjectives. Okay? And our objects are nouns. Okay? So when I'm thinking of a thing, it has to be a noun. It has to be an object. A thing is not a measurement. Okay? And this is going to become important in a little bit. Okay? Or not even in a little bit. It almost effectively becomes important immediately because it's how we manipulate these things. And I didn't mean to repeat the word thing there. It just happened. So, let's first attempt to use this. Okay? Because one of the things that you will be expected to do is to manipulate this conversion factor, and you are required to memorize it, so work on memorizing it. So let's look at a simple question. How many oxygen atoms are in 0.240 moles of O2? So if we go through and look at this, I am looking for atoms of oxygen. And I'm writing out oxygen as a whole word here, and we'll see why in a little bit. And what are we starting with? Well, we're starting out with 0.240 moles of O2. Okay? Moles are a counting thing. So in this case, what is the thing associated with this? Well, it turns out that chemists are being a bit lazy here, because you're probably lazy about it too, and we've left out what the thing is in this case. O2 is the substance, not the thing. Okay? Is it an atom of O2? Well, what is an atom? An atom is one, for lack of a better word, atom, okay, or piece. If we take a look at O2, is it one atom? No, it's one element, but it's two atoms. So that thing is actually a mole of molecules. So if we now add that word into this, molecules, we get mole of molecules, 0.240 moles of molecules. Okay, now, what do? Well, moles of molecules of O2 are not the same thing as atoms of oxygen, right? So how could we go through and set up this conversion? Well, the reflex might be to be like, well, I need to get rid of moles, yes? Yes, I do. And what do I want? Well, I want things. My thing in this case being atoms of oxygen. Okay, so I could go through and do my conversion, but I have to make sure my full unit here, this is moles of molecules of O2. And if we tried to drop Avogadro's number in here, we'd get 1 mole of molecules of O2, 6.022 times 10 to the 23rd atoms of oxygen. We go, okay, well now we've got this figured out. This is why units are useful. Do your units cancel and align so that you get your answer? You'd be like, well, of course they do, Mike. See, moles of molecules of O2, moles of molecules of O2, those cancel, and I'd be left with atoms of oxygen. Did you properly use the conversion factor? That's a much harder question. Okay? Note, when we look at that conversion factor in that red box, it says 1 mole of things is big number of things. What is the thing in our conversion factor down here? Okay? Because note, things, Things, is spelled the same on both sides of that equation in the red box. What is the thing in our expression? If you want to say that thing is atoms of oxygen, is that the same as molecules of oxygen? Because if it's the same, shouldn't it be the same word? Oh, it should be the same word, but it's not. Which means what I just put in that black box is entirely false. Okay? I am literally shoving numbers into this, just saying they work. Okay? This is the exact mistake you need to not be doing. Okay? And for those of you being, well, you should have shown me correctly first. No, because all you would have done is just keep doing the same, forcing it in. You have to see your units. Okay? Don't start dropping numbers in immediately. Evaluate what you have. Moles of molecules of O2. If I want to use that red box, the thing would be molecules of O2. Yeah? Now if I put the numbers in, 6.022 times 10 to the 23rd, now the units will cancel here. Moles of molecules of O2 cancel with moles of molecules of O2, but now I have molecules of O2. Are molecules of O2 the same thing as atoms of oxygen? This is where knowing your nomenclature and what we said, the symbol, of when we should use O2 versus O comes into play. An atom of oxygen could be written as an atom of O. Atoms of O are not the same thing as molecules of O2. We need another conversion factor. That conversion factor needs to cancel molecules of O2, and it needs atoms of O. Where do I find a conversion factor that relates those? Turns out it's 2 to 1. That conversion factor came from the chemical formula. The conversion factor that allowed us to convert molecules and moles came from Avogadro's number. Avogadro's. Oh man, I just butchered the spelling on that. Avogadro's number. Okay? So we have to think about where these things are coming from. The black one, we had to memorize. The blue one, we have to interpret on our own. That interpretation is very often coming from nomenclature, which is back in chapter 6, being able to derive what the names and formulas are. Okay, so if you have any underlying weakness, it's gonna bite you. This is why we pushed to make sure that you understand those pieces. Okay, so we're tracking the units. Don't start fudging the units just because you just want to do one calculation. Write the units as they are and manipulate through them. Okay, so let's look at, well, that was a useful segue. Okay, why use this conversion factor? So let's delete that for the moment. Okay, and this was something that the video was getting at. If we're looking at the point of Avogadro's number, which is what we were getting at with the previous sequence of slides, was looking at mass and numbers of particles. If I want to measure out 1 atom of sodium, how many grams is that? Okay? So I would need a conversion factor between atoms of sodium and grams of sodium. Well, that conversion factor doesn't exist. Okay? We don't have a relationship between mass and or grams and atoms. But we do have on the periodic table a relationship between mass and atoms, and that mass unit was AMUs. And we could pull it up. I think it's 22.99, but I'm just going to say 23. Thank you for pointing out that that should be an A, not a G. Okay, there's 23 AMUs of sodium per 1 atom of sodium. AMU is not grams, so what do we need? We need another conversion factor, AMUs and grams. And we would have to go and look that conversion factor up. And it turns out it's something like 1.661 times 10 to the negative 24th grams is 1 AMU. Okay, and we end up coming up with a gram value that is astronomically tiny in size, right? Okay, because you're 23 times 1.661 times 10 to the minus 24. So an incredibly small number. Okay, the more relevant spin on this is to say, well, if I'm going to run an experiment with sodium, I cannot realistically do an experiment with a single atom. So this is not realistic. Let's just say not real, because I can't spell for the moment. Okay, so what we're going to switch it up and say is, well, how about I measure grams of sodium? Okay, how many atoms of sodium would go into that if I did grams of sodium? So let's say, just for giggles, I'm going to do 23 grams of sodium. Okay, so that is now a measurable amount. Okay, and if I'm going to go through and do that, how many atoms of sodium would that come out to be? Well, grams of sodium would need to cancel. Okay, to get to atoms, I have to go through AMUs. So we're looking at that relationship. Actually, it's just 1 there. I can get away with it. 1.661 times 10 to the negative 24th grams of sodium is 1 AMU. Okay, and then 23, whoops, helps if we write our units. See, this is why we write units first. We want to get rid of AMUs, and we want atoms of sodium. One atom of sodium was 23 AMUs from our periodic table, and we could go through and we'd punch this into a calculator and we'd get an answer. Interestingly enough, the answer that we would get would be 6.022, because I'm good at math in my head, times 10 to the 23rd atoms of sodium. Well, cool, so I just be using this really, really big number that, arbitrary, big, crazy number that has no real... Isn't that the same thing as Avogadro's number? Yeah, it is. So what if I used that conversion factor instead of going to atoms of sodium? Because that number is a ridiculous number. Okay, instead of being atoms of sodium, I went into moles of sodium. Well, that conversion factor, 6.022 times 10 to the 23rd, 1. And if we went to this all out, what do we get? We end up with 1 mole of sodium. So if I start with 23 grams of sodium, that is 1 mole of sodium. Okay, so if we simplify that all out, because that top one was not real, not useful, so let's get rid of all that, and let's simplify that all the way down. I did a whole bunch of work, and I said that 23 grams of sodium can become equal to 1 mole of sodium. That looks like I could do a relationship where I say 23 grams of sodium over 1 mole of sodium. And that looks an awful lot like a conversion factor. That looks an awful lot like the conversion factor that came from the periodic table when we were looking at AMUs. That's interesting. It is. So why would we do that? Okay? Avogadro's number is designed for the explicit purpose to get rid of the AMU to gram conversion. It is designed to completely inverse it so that we don't have to worry about it at all. Which means when I go through to look at the periodic table that tells me an atomic mass can also be given as a molar mass. Except when I shift from an atomic mass, which is units of AMUs, who the hell knows what an atomic mass unit is, per atom, it could also be more usefully written as grams per mole. The whole point of Avogadro's number is to take those numbers for masses on the periodic table, okay, with bizarre just number of protons and neutrons in an atom, and scale that up so that now it is just reading right off the periodic table the grams for an absurdly large number of atoms, okay, which I'm going to define as a mole. Okay, that is pretty phenomenally cool. That's the point of Avogadro's number. Our point is to make the numbers on the periodic table more useful, right? Or actually useful, because we can't use AMUs. We don't have a balance that's going to tell us the AMUs. That balance doesn't exist. Okay? That's the beauty of Avogadro's number. Okay? So, let's take a look at how we can use this. If I asked the first question of atomic mass for copper 2 nitrate, what you might tell me to do is go to the periodic table, find the atomic mass for copper, the atomic mass for nitrogen, the atomic mass for oxygen, and then add them all up. And that would now be the atomic mass for copper 2 nitrate. Okay, cool. But what happens if I make it molar mass? Okay, well, if we didn't have Avogadro's number, what would we have to do? we would have to convert the atomic mass of each of those things and scale that up to whatever arbitrary system we're at. Okay? That's a lot more work. Because we have Avogadro's number, all I have to do is go to the periodic table and say, what is the mass of copper? Okay? What is that mass? What is the mass of nitrogen? What is the mass of oxygen? And now all I have to do is add them up. Okay? And here's where I'm going to run into a problem because I don't have a periodic table handy. No, I don't. And ta-da, I got one that fast. So when we go to the periodic table, we will hopefully be able to see, depending on your periodic table, is that copper is 63.5. Okay? And we're going to leave the units off for the moment. Nitrogen is 14.0 and oxygen is 16.0. Okay? What are the units with those? Okay, well, if we asked for atomic mass, those units would be AMU, AMU, AMU for each of those individual atoms. But because we're asking molar mass, those units are now grams per mole. Grams per mole and gram per mole. Well, per mole of what? Per mole of copper, per mole of nitrogen, per mole of oxygen. Okay? When I look at that individual formula, now I want to ask myself, because it's molar mass, if I have 1 mole of this substance, how many moles of copper would I have? Well, I'd have 1. So, times 1 mole of copper gets me 63.5 grams. Times how many moles of oxygen? Sorry, we're looking at nitrogen. Right? Because of this formula, I know that 2 applies inwards, and I have 2 moles of nitrogen. So 2 times 14, I get 28.0 grams. How many moles of oxygen? Well, the 2 applies inwards, and I already had a 2 there, times 4 moles of oxygen. Wish I could do that in my head. 3264.0 grams. And now if I want the molar mass for that substance, what can I do? I just add those numbers up, and if we can do that correctly and in a reasonable amount of time, we should find that the answer is 1.55 grams of copper nitrite per 1 mole of copper nitrite. And we now have a conversion factor that gets us a mass at a reasonable scale, and it tells us how many numbers of copper nitrites are present in the form of moles. Why go to moles? Well, if we didn't go to moles to get a mass that was measurable, we'd have 6.022 times 10 to the 23rd, or somewhere on the order of that number of particles. That's stupidly high. Okay, so we literally invented moles as a term to simplify our calculations. Okay, and that's kind of neat. Okay, so how could we use this information? Well, let's go through and try and solve a question. In this case, I'm being asked for the grams of our copper 2 nitrite. Notice we made this question a little bit more difficult because we gave you the name and not the formula. So first step, you would have to recognize that you know copper, you know nitrite is NO2, you know nitrite is a -1, copper is a +2 because it's found within the formula. I need 2 nitrites to balance it. There's my copper 2 nitrite. What was I given to start with? We were given moles of copper nitrite. Okay, how many moles? 0.532 moles over 1. Why am I placing that in the numerator? That's not a mass. You would be correct. That is not a mass, but it is for the substance I'm aiming for. So I can use clues within the unit to help me place where my answers should go or where my work should go. Okay, copper 2 nitrite is in the answer numerator. It's going to be in my work in the numerator as well. Okay, if I'm now going to go through and solve, I need moles of the copper 2 nitrite to disappear, so I have to place that in the denominator. And in the numerator, I want grams of copper 2 nitrite. So now the question becomes, does this conversion factor exist? Okay, so we could jump to the front of the exam and say, is it there? No, it's not. Okay, so where would I find it? Well, this is what makes this unit so much more challenging. You have to know where to find this information. As you're being clued to up at the top, okay, you're being told that you need to find that information on the periodic table, and that was actually the question that we just solved, where we went through and said it was 155 grams per 1 mole of our copper nitrite. As I tried to write in the formula and wrote it wrong. Copper nitrite. Where does the 155 go? Not on top, not on the bottom, with grams. Okay. Now what happens in our calculation? The moles of copper 2 nitrite cancel, and all we have to do is go through and multiply these two things with each other. Okay. In that multiplication, we should get as an answer 155.5 times 0.532. Our calculator should spit out the number 82.726. I'm going to erase the page number 24 for a moment. Okay, grams of copper 2 nitrite, which of course is wrong because we haven't considered sig figs. We're only allowed 3 sig figs. Our answer is 82.7 grams of copper 2 nitrite. Okay, that is our process. Okay, as we continue through this unit, it's only going to become more and more challenging and difficult. So we need to be comfortable with that process so that we can spend some time finding these pieces of information and memorizing that aspect. This is why I told you the process and you needed to follow it. Okay? So with that, I'm going to give you a second to try and figure out how many grams are in 2.55 times 10 to the 23rd atoms of lead. So I'm going to recommend that you take a pause for just a second here and spend some time to set up your work. So, did you pause? Did you figure it out? Okay, let's set it up. What are we being asked to solve for? We want grams of lead. It's helpful if we immediately convert across into our symbols. Okay, what are we given to start with? We're given 2.55 times 10 to the 23rd atoms of lead. So if we write our unit in, okay, I'm placing the lead as a substance in the numerator because as a substance it shows up in the numerator in my answer. Okay, this is going to be over 1. 2.55 times 10 to the 23rd atoms of lead. Okay, so now I've done step 1 and step 2 of our conversion process. This was again one piece of information in my overall solve. So I've taken that one piece and placed it in. Okay, so now I need to do a conversion. In that conversion, atoms of lead needs to appear in the denominator, and I want it there so that those units can cancel each other. Ideally, I also get grams of lead appearing in the numerator. Okay, that would be my ideal situation, because if it showed up there, then I've got my conversion factor set up and ready to run. Okay, and because I don't like that color being red, I'm going to write grams of lead. So now I have to ask myself, where is there a conversion that relates mass and the number of atoms of a substance? Okay. Well, that conversion factor, unfortunately, does not exist. Okay. Because it doesn't exist, I'm going to have to change one of those units, either the grams of lead or the atoms of lead. Because I want to cancel, because it's always nice to get rid of things, I'm going to, instead of going into grams of lead, I'm going to go into something else. Well, now the question is, what else do I want to go into? Okay. Well, thankfully at this point, there's only one other thing you could convert to, because we only have one. That's a lie. There's two things you could convert to. We could take the atoms of lead, okay, and we could convert it to AMUs of lead. We could also take the atoms of lead and we could convert it into moles of lead. Okay? Either of those conversions will work. Okay? My preference is to do the moles of lead, because that is a conversion factor that I'm required to have memorized. That is Avogadro's number. Okay? In that memorization, I have to know what thing goes with what. The moles is the larger piece, which means it's just the one. Atoms is all the things that go into that. 6.022 times 10 to the 23rd atoms is 1 mole. Okay? So cool. That's awesome. I've now incorporated a new piece. For those of you wondering about the other conversion, I will do that one in a little bit, but we're going to skip it for the moment. And we'll move to the next aspect of this. Moles of lead need to become grams of lead, okay, in our ideal scenario. If we match color coding, where do I find the mass of lead related to moles of lead? Well, that is found on the periodic table. Okay? And when I go to the periodic table to find that, I find that the mass is 207.2 grams of lead being equal to 1 mole of lead. I do want to point out, because I have seen students start to, I have seen students start to reference other numbers. When we look at lead on the periodic table, we'll have our 207.2, and then we also have this 82 floating up there. Okay? Remember, the 82 is the atomic number, not mass. The 207 is our mass. This is why we addressed those things back in Unit 1 about their meanings. Okay? So if we track our units now, the moles of lead cancel the moles of lead. The answer I would have left with, or the numbers I would have left with, would be all of those, and I can now punch it into the calculator. And I'm going to intentionally punch it in incorrectly here, so that we can actually see what the end result is, or what some of you will likely get. Okay. Some people will be very likely to get as an answer 8.773. I can't quite read my calculator. 8 times 10, and actually we're going to fix this a little bit. E 47. Okay. So I'm going to erase all the work underneath. So if you wanted that, you might want to pause so you can write it down. Okay. How did I get that number? Okay, well, if we go through and look at the calculation, 207.2 over 6.022 times 10 to the 23rd times 2.55 times 10 to the 23rd. Okay, and if we enter that into the calculator, we might get this number written out here. Okay, written another way, that number is 8.77. I'm just going to leave it 8.77 times 10 to the 47. That E symbol is referencing that E, that times 10. Okay? Well, if we do some manipulations, we should recognize that this times 10 to the 23rd is the same on the top and the bottom and should cancel out. Okay? So if it cancels out, we should not be seeing a power of 10 that is to the 47. So what happened? Okay, what happened was a calculator mistake. This value in the denominator, the only part that when you entered into the calculator that actually went into the denominator was the 6.022. The times 10 to the 23rd, you entered inadvertently into the numerator. If this is you, that is okay. Please contact me so that we can make sure you're entering that correctly. Okay? This is following the order of operations in a calculator, PEDMAS, or something else that I don't know the name of, or whatever it is. We have to remember how our calculator calculates, and we have to ensure that we enter it correctly. Okay? So if we actually follow how the calculation was supposed to be run, the number that we get correctly is 87.7 grams of lead. Okay? And that is with the proper sig figs. Okay? And that would be our final answer. To get us an idea of a check on this, if you're good with relationships here, we're looking at a number that is less than a mole. Okay, a mole was 6.022 times 10 to the 23rd. 1 mole of lead should be 207. So we should be getting a number less than 207. Okay, you can do some more estimation skills after that if you really want to, but we're at least in that ballpark. I also said that I was going to go through and show the other calculation, so I'm going to pause the video and write all that work out so that you can see the other calculation down underneath. So if you remember when we were talking about our conversions, it was that black conversion, or the blue one in the middle, that we said there were two options. We could go atoms to moles, or we could go atoms to AMUs. If we went atoms to AMUs, that's shown in orange underneath. Okay, that sets up a new problem because now we would be going AMUs to grams as opposed to moles to grams. So we get a slightly different conversion system here. Okay, if we break these down, I want to pause again. So if we break this down again, the red stuff is the same given information. When we were working through our conversions, we could have gone black, or we could have done the orange conversion underneath, which I've also got boxed in green. So the black conversion was a number-to-number conversion, atoms to moles, a very small number to a very large number. The one underneath is a mass-to-number conversion, okay? And that mass-to-number is a different number, if you will. We're looking at atoms number versus moles number. That's the same thing as we've done up here. Okay? Those are effectively the same conversion. You're just doing it to different numbers of particles. Because we picked such a good number-to-number relationship to to undo the mass-to-mass relationship, we don't have to stress about which way we go. Okay? This does introduce one of the issues within these conversion processes, is depending on which conversion you see, your work will look different than somebody else's work. Okay? And that is okay, as long as you're tracking the units and you're coming up with the proper conversion factors. Okay? This provides a lot of wiggle room that freaks a lot of people out. If you're one of those people that just needs to know this is how you do it because there is a formula, you're in the wrong class. Sorry. The tutoring center, which I've been told is open at least for 1 week here, does have what is known as the mole wheel. I'll try and get a digital copy of that in case they end up closing down, and I'll post that to Canvas, because what that really does provide is absolute paths, so there's no wiggle room or thought needed behind that process. Kind of hate to call it like that, but that's the way it is. And so with that, we've got two processes, so we've got another little work going on with this. So let's go ahead and try another one. What is the mass? Let's see. We're going to make this one a little bit more difficult and easy at the same time. Instead of being a single molecule, okay, because that one tends to trip people up, I'm going to make it 6 molecules. Okay. So what is the mass of 6 molecules of sulfur dioxide? The molar mass of sulfur dioxide is 64.07 grams per mole. Just giving you that to make it a little bit easier. So again, I'm going to recommend you hit pause here and try and set up your work to solve this. I'm going to assume that you were still listening because you needed a little bit more help. So step 1, what are we solving for? Okay, what is the mass in grams of sulfur dioxide? Okay, if we were given 6 molecules, I hate it when I split it like that, 6 molecules of sulfur dioxide, and we're also given a second piece of information. We're told 64.07 grams per mole. Which of those two pieces of information we use is largely up to you. But I'm going to recommend, again, you hit pause and see what you can come up with. And I guess you still need a little bit more help going on with this. I would argue we should use the green one first, because if we look at our answer, we want grams of sulfur dioxide. Okay? 6 molecules of sulfur dioxide doesn't have anything about grams in it. There's no mass in here. It's not there. But I do see a gram in there, so mass is involved in this one. So I'm going to use that one first. I want the grams to be in the numerator, because that's where it shows up in my answer. That slash meant division. As soon as we see that, you should be drawing that line horizontal, full horizontal, so that we see a clear numerator and denominator. The 64.07 is closest to the grams, so that means I'm going to place it closest to the grams unit, and 1 goes in the denominator. Okay, so again, I'm going to give you a second here to pause to see what you can come up with for the rest of this solve. And away we run with the rest of this. Okay, in my next step, okay, because this was a given piece, in my next step, I want to get rid of moles of SO2. The moles of SO2 in my given information is in the denominator, so I need to place it in the numerator. Okay, I'm not given moles of SO2. 6 would be an improper usage here. This becomes a common misconception. Okay, molecule is not the same as mole. Okay, and this is why when I go through and do an abbreviation for molecule, you'll see me write MLC, not MOL, because they're different things. Okay, so I'm not given the moles of sulfur dioxide. I'm going to have to come up with some kind of conversion. Okay, I could go to grams. So moles to grams. That should immediately send up alarm bells because I've already used it. If I've already used it, that's probably not a good conversion to do. Okay, so I could do moles to atoms. I can't really use atoms because I'm looking at sulfur dioxide. Okay, it's not an atom, but I could go to molecules. So I will go to MLC. Okay, so the conversion between moles and molecules is going to come from, really wanted this color-coded to try and differentiate MLC. This MLC is going to come from Avogadro's number. I'm having a hard time spelling that. Avogadro's number. We have to remember the placement of where the number goes. It goes with our molecules, 6.022 times 10 to the 23rd molecules. It's 1 mole. That piece of information was memorized. Okay, so cool, that sets it up where my moles of sulfur dioxide cancel. Okay, but now I've got molecules, and I did a bad job because I didn't actually write out SO2. I don't want molecules of SO2. So I know the molecules of SO2 needs to show up in the numerator. Okay, so now again I ask myself, is that just given information? Well, actually, yeah it is. It's actually right there. Molecules of SO2. So I could drop in the 6. Okay, what goes in the denominator? 1, because that was a single given piece of information. Was 6 molecules of SO2. Okay, now what happens? The molecules of SO2 cancel. The moles of SO2 canceled with the moles of SO2. And now I'd have my work lined up where if I entered this into the calculator, I would get my grams of SO2. So now all I got to do is enter it into the calculator, and I get a whopping 6.3836 times 10 to the negative 22 grams of SO2. So an incredibly small number. That seems too small to be real, so let's think about it. Okay, 6 molecules. Well, molecules are incredibly small, so their mass should be small. If I only have 6 of them, the mass should still be small. So yeah, okay, it should be a really small number. Should it be that small? Right. Well, I've got a 10 to the negative 23 in the or 10 to the 23rd in the denominator, which means it's going to be really, really, really small. And there isn't really anything to contradict that division. So yeah, that's probably right. Okay. The last thing that we should consider would be sig figs. And admittedly, this is one I completely botched the sig figs on, because 6 is such a small number that we would consider that infinite. So how many sig figs here? Arguably on a multiple choice, I'd probably only give you 3, and you wouldn't have to worry about it because you wouldn't see other answer choices where they had those other sig fig options in there. So 6.38, I don't have to round, right? Yeah, 6.38 times 10 to the negative 22 grams of sulfur dioxide. Okay, and that should be our answer. Okay, that's an hour now of cranking calculations. You're probably getting sick and tired of it. And because you know me, you might as well do another one. So yeah, seriously, do it. Work through it. Set up your work. See what you can come up with. And remember, it's not the answer that you want. You want the process. You won't see the same question again. Follow your process. This becomes a more challenging conversion. So let's go through and look at it again. What we're given is mass, and we're given F2 as a substance. What we're ending with is atoms and F as a substance. So we have changed both the substance and the measurement unit, which means minimally we have 2 conversions that we've got to go through and run. Okay, so make sure that you're taking that into consideration when we run through and do this. Okay, I would argue it is easiest to deal with the well, actually no, I don't actually have an argument for which one's easier to deal with first. Okay, I'm actually going to make the argument that it's easier to deal with the substance conversion first. So I'm going to write substance here. So I want to go from F2 into F. Okay. To do the conversion, though, I have to have a measurement unit associated with it. When we're looking at dealing with substances, we have to be looking at either atoms or molecules. Okay. So atoms of F, molecules of F2. Okay. Now I have a proper kind of substance conversion there. So now how do we set that up? Okay, or where do we find that? Well, that substance conversion is found in the chemical formula of F2. There are 2 atoms of F in every 1 molecule of F2. Okay? This should set up a problem for us because if we go through and look at this, yes, this gets us atom of F, but we've introduced this new conversion of molecules of F2 that doesn't convert with anything. Okay? So I'm going to have to do another conversion. So now what I might try and launch into would be my measurement conversion and see what I can come up with. Okay? The measurement doesn't disconnect from the substance though, so just be aware of that. So it's going to be grams of F2, and ideally what I would want would now be atoms. Atoms of F I already got. I want to get rid of the other substance or the other measurement, molecules of F2. Okay? Does that conversion factor exist? Is there a relationship between grams and molecules? No. Okay? There is a relationship between molecules and AMUs. Okay? There's also a relationship between grams and moles. Okay? So we have to decide which one we want to do. My reflex is to always go through grams and moles. Okay? Moles tend to be the most powerful thing, so reflexing into moles is probably a good idea. Okay? Where do I find the relationship between grams and moles? That conversion factor is now found on the periodic table. For fluorine, we're looking at 17, I believe. That's a lot. I can't read it from here. 19? 19. Is 19, but it's F2. There's 2 of them, which means we get 38 grams per mole. The 38 shows up closest to the grams, so we'll place it there. Moles. If we follow our units, okay, the grams of F2 long distance cancels. Fantastic. But now I've got moles as a unit that I don't want, which means I need to launch into another conversion factor. In that conversion factor, I know the moles of F2 needs to disappear, so I'll place it in the denominator, and I need molecules of F2 to also cancel, so I'll place it in the numerator. Where's the relationship between the molecules and moles? Is that a conversion factor that exists? Yes. That conversion factor is Avogadro's number. Simony frickin' Christmas. That thing, number. Okay? For those of you saying, but that said atoms, remember it said things. Okay, that was our big edit. Molecules are things. So when we're going through and looking at this, this is moles of molecules of things. 6.022 times 10 to the 23rd molecules is 1 mole of molecules of F2. What happens with our units? The moles of molecules of F2 cancel. The molecules of F2 cancel. If we now look through all of the units canceled in our first thing, so there's nothing there, there's nothing there. The only thing left is atoms of F, which is exactly what I want for an answer, which means I can now enter it into the calculator. And the number we should get would be 7.13 times 10 to the 22nd atoms of F. Right? This is a interesting question in that there are a couple places where 2 wrongs make a right. It is very common for students to screw up the conversion factor in orange and only say this is 1 over 19. Okay? If they also screw up and forget this conversion, everything works out nicely and we don't have to worry about it. Okay? So 2 wrongs can make a right in this case, unfortunately. Make sure your unit work accounts for all of the conversions appropriately. Sometimes it works out nicely, sometimes it doesn't. If you're at a 50-50, that's not a good exam score. I want you to do better than that. Make sure your units and the numbers that you're using for each of your solves works. When it comes through to showing work, this is the work that you should be showing. I know this is a lot of stuff, but it's explaining where each of those pieces come from and why you're allowed to use them. If you are finding that the only work that you are showing is what's written through the middle there, you are probably not going to do well on the exam. Okay? It's unfortunate, but that's the way it's going to work. Need to be identifying all of the individual questions that are being asked along the way to go through and solve. Okay? With that, we finished all I really want to talk about for the moment in Chapter 8, which is really just dealing with our mass molecule conversions. The next video is going to go into bringing in chemical equations, which is really just another substance conversion that we've already addressed here. It's just interpreting it from a chemical equation as opposed to a chemical formula. Okay. With that, I hope you're practicing. I hope you're staying safe. If you've got questions, remember to post questions, send me an email, all that kind of fun stuff, and we'll get you figured out and sorted.